In mathematics, a whole subgroup of a finite group G is a subgroup whose order is coprime to its index. They were introduced by the group theorist Philip Hall. Definitions: a whole divisor of an integer n is a divisor D of n such that D and n, D are coprime. The easiest way to find the whole divisors is to write the prime factorization for the number in question and take any product of the multiplicative terms, including 0 of them for a product of 1 or all of them for a product equal to the original number. For example, to find the whole divisors of 60, show the prime factorization is 2235 and take any product of 3, 4, 5. Thus, the whole divisors of 60 are 1, 3, 4, 5, 12, 15, 20, and 60. A whole subgroup of G is a subgroup whose order is a whole divisor of the order of G. In other words, it is a subgroup whose order is coprime to its index. If pi is a set of primes, then a whole pi subgroup is a subgroup whose order is a product of primes in pi, and whose index is not divisible by any primes in pi. Examples: any solo subgroup of a group is a whole subgroup. The alternating group A4 of order 12 is solvable but has no subgroups of order 6 even though 6 divides 12, showing that Hall's theorem cannot be extended to all divisors of the order of a solvable group. If G equals A5, the only simple group of order 60, then 15 and 20 are whole divisors of the order of G, but G has no subgroups of these orders. The simple group of order 168 has two different conjugacy classes of whole subgroups of order 24. The simple group of order 660 has two whole subgroups of order 12 that are not even isomorphic. The normalizer of a solo 2 subgroup of order 4 is isomorphic to the alternating group A4 of order 12, while the normalizer of a subgroup of order 2 or 3 is isomorphic to the dihedral group of order 12. Hall's theorem. Hall proved that if G is a finite solvable group and pi is any set of primes, then G has a whole pi subgroup, and any two whole pi subgroups are conjugate. Moreover, any subgroup whose order is a product of primes in pi is contained in some whole pi subgroup. This result can be thought of as a generalization of Solo's theorem to whole subgroups, but the examples above show that such a generalization is false when the group is not solvable. The existence of whole subgroups can be proved by induction on the order of G, using the fact that every finite solvable group has a normal elementary abelian subgroup. More precisely, fix a minimal normal subgroup A, which is either a pi group or a pi group as G is pi separable. By induction, there is a subgroup H of G containing A such that H A is a whole pi subgroup of G A. If A is a pi group, then H is a whole pi subgroup of G. On the other hand, if A is a pi group, then by the Shor-Zassenhaus theorem A has a complement in H, which is a whole pi subgroup of G. A converse to Hall's theorem. Any finite group that has a whole pi subgroup for every set of primes pi is solvable. This is a generalization of Burnside's theorem that any group whose order is of the form PAQB for primes P and Q is solvable, because Solo's theorem implies that all whole subgroups exist. This does not give another proof of Burnside's theorem, because Burnside's theorem is used to prove this converse. Solo systems. A Solo system is a set of Solo P subgroups SP for each prime P such that SPSQ equals SQSP for all P and Q. If we have a Solo system, then the subgroup generated by the groups SP for P in pi is a whole pi subgroup. A more precise version of Hall's theorem says that any solvable group has a Solo system, and any two Solo systems are conjugate, normal whole subgroups. Any normal whole subgroup H of a finite group G possesses a complement, that is, there is some subgroup K of G that intersects H trivially and such that HK equals G. This is the Shor-Zassenhaus theorem.